Hey, hello and welcome back, everyone. Moving on to absolutely my favorite section in this entire book. Competes closely, I guess, with the dynamics section, but in many ways, this is Calculus 2. This is the whole reason why we spend a second semester in calculus, and that reason is the Taylor series. Okay, but we're going to be a little bit broader than that for today. We're also going to analyze power series, which is kind of the general form of all this series that includes Taylor series, as well as generating functions, which are kind of Taylor series and power series flipped on their head. Rather than thinking about them as series representations of functions, we're now with a generating function thinking about a function representation of a series. And so in some ways, this entire semester we've been working with a continuous calculus and its best friend, the discrete calculus. But you'll notice what's going on with both of these, the way I've drawn them. This word series is, of course, an object of discrete calculus. And this word functions is an object of continuous calculus. So even though we've been spending the whole semester showing how both the continuous and the discrete calculus work under approximately the same rules, you've got like these finite differences that kind of behave like derivatives, and the sum is like the discrete integral and so on. Today is a true synthesis that's showing that the objects are indistinguishable if you interpret them in specific ways. You can think about discrete calculus objects as functions, and you can think about continuous calculus objects as series. And it's one giant broader picture of mathematics that we're going to achieve today. And so to motivate this a little bit more, maybe you've been wondering in the past about Euler's identity. You're going to have to wait one more video for the most part. We'll eventually get to Euler's identity and proving it. But we've been referring to Euler's identity a bunch, all the way back with polar complex numbers, like the third section of the book, as well as when we were working with trigonometric integrals. We really referred to Euler's identity a lot, and that says that an exponential to an imaginary number times an angle measurement theta is equal to cosine of that angle measurement plus I times sine of that angle measurement. And that's a completely unintuitive equality, and yet it's true. We're going to see why it's true using the power of the Taylor series in the next video. Not this video, but we'll see why it's true in the future. We also saw way back when we were working with kind of the first power rule for sums. How could I sum the first n terms of m to a specific power k? Right, this would be like the indefinite integral of x to the k, but we know that one is really easy. It's x to the k plus 1 over k plus 1. It's a lot harder in the summation world. Remember, there was kind of that generalized version that had the Bernoulli numbers show up, but we didn't like that version. And so what instead we created when we were trying to sum using partial fractions, we created this kind of limit definition of the generalized first power rule, where we take a limit as x went to 0 from below of k derivatives of a very specific function. And it turned out that just this upper bound n showed up inside of a function. And so somehow we're relating a specific summation to a specific collection of derivatives against a function and then limits. So there's really a huge synthesis of the continuous and discrete calculus happening here, right? Derivatives are a continuous calculus object. Limits are a continuous calculus object. And yet the left-hand side is purely a discrete calculus object. So there's just so much synthesis going on between the discrete and the continuous, as well as the complex numbers here. And they all revolve around our ideas of power series, which includes the Taylor series and generating functions. So let's actually just analyze what a power series is before I get into maybe more specific definitions. And really, we should just be focusing in right here for now on the power series. Right here, what am I looking at? I'm looking at an infinite series. That's important about this. And the infinite series is going to start at 0 and end at infinity. And you can basically think, if I decide to just put a box around the infinite series and a sequence that's inside my series, that box looks just like the infinite series we know and love, and that we've been studying for quite a while, right? This can describe maybe an equilibrium of a discrete dynamics. We can also just think about it as relating to infinite integrals and proper integrals, using all of our convergence tests and everything. But we're modifying it just a little bit today. We're modifying it by multiplying each term of our series by what's basically a polynomial. Multiplying each term of our series by x minus x0 to the nth power. And yeah, if you expanded that out, you just get a very specific collection of polynomials. I mean, it would look like the Pascal's triangle polynomials, right? Because these are really binomials that have been condensed. And so we're multiplying each term in our series by this x minus x0 to the nth power. But because there's an x right here, and we're leaving that x as a variable, what we get out of this infinite series, so long as it converges, which is why our convergence tests are important, we get a function of that variable. So there's a variable here and that variable is also there, which I suppose is also here. Okay, so we're putting a variable into an infinite series, and we're assuming that the infinite series converges maybe for specific values of that variable. Now this x0 has kind of been hiding out, and I haven't really talked about what that is. This is just a number, a real or complex number, where we like to think the function f of x, which really is our power series, behaves nicely at. It's kind of a special point. So this is some special real or complex number that we have reason to believe our function behaves well at. That's going to be determined for us, or maybe we'll determine it for ourselves, but using some good intuition. And that number is just called the center of the power series. We'll see why it's called the center a little bit later. But it's just some value that's predetermined for us. You know, you might have a power series centered at 0, very common. It may be centered at 1, also very common, but you could center it at 27, negative pi, 246 plus 6i. You know, you could put it anywhere in the complex numbers, and that would just like show up in these terms that are included in the power series. Now, there's also something else hiding behind the scenes in this power series that we haven't really discussed. It's not there. That defines the rule for the function, but we should recall functions are more than just rules. Functions are domains and codomains. And if we look at the domain of our function, it has its own sort of funky notation. It's b subscript r of x0. Now that x0 is still our center, so this is the same x0 here. But that b sub r is very special. It's called the open ball of radius r, and the x0 here it's called a ball centered at x0. That's in fact why we name x0 the center, is because it actually centers our domain of the function. And what does the ball actually look like? Well, it looks like a collection of values x. I could have used any variable there, but we'll just say values of x. Maybe they're real valued, such that the absolute value of x minus the center is less than or equal to r. This is a weird way of writing. It's a very mathematical way of writing. This just says all numbers within a distance of r from the center x0. That's why it's called a ball, right? If you choose some point, you look at all points within some distance of that other point, that's always going to give you, well, a sphere in 3 dimensions, circle in 2 dimensions, and an interval in 1 dimension. But really a ball is what we refer to that as. So ball-like object in higher dimensions. And this subscript that I haven't really discussed, the subscript r here that I've referred to as the radius r, as far as the series is concerned, here it is, and you can actually calculate it. It's a value that's uniquely calculable just from the sequence an. You calculate the limit. This is actually just 1 divided by the ratio test limit, or it's equivalently 1 divided by the root test limit. So in fact, the reason why those ratios and root tests were important is because they kind of tell you what the domain of power series are, because the domain is only where the series is going to converge, and the series is only going to converge when the ratio or the root test actually converges, and the ratio and the root test converge specifically when you look at their reciprocal and you make it a radius, basically a radius of the points you're allowed to put into the specific power series. Now that's all very, very abstract. You really should just think about it as this object where you can calculate this number r from the sequence an, and then we're going to work with all of those. We'll talk about why our radius convergence is what it is. So let's go ahead and say we establish that the radius of convergence is one of these two limits. They will always converge to the same value. You can compute either of them. The reason why it's radius of convergence, I kind of hinted at that. The proposition here, what is the statement I'm making? The radius of convergence guarantees that the power series will converge, right? Because at the end of the day, this is an infinite series, so we care about its convergence properties. The radius guarantees it will converge for all values of x that actually exist inside of this ball. That's the reason why we care so much about the radius of convergence. It turns out if you just decided to grab any number here, like maybe I put 17 in there and suppose x naught were 0, but the radius were only 16, then you would find out that this is a divergent series. And so the radius is just kind of giving you that check to say, all right, we can put variables in, but the variables have to be constrained somehow. And I have a remark that describes what a ball looks like in the real numbers. So if I'm working with the real numbered balls, that is this particular image, you can see I've displayed the center x naught at the middle. Here's my x naught. And then I've moved out exactly 1 radius in each direction. and I'm not going to include the ends. The endpoints are going to stay open. That's why I sometimes call it an open ball. You can imagine almost like if I had a disc and I turned it on its side and I were looking at the disc sideways, or even on a turntable. If I were playing a record, this is like me playing a record on a turntable, and I'm just seeing the record from the side, but you could imagine the radius of the record is still well defined even when you look at it from its side. But of course, in the complex numbers, when everything is two-dimensional, this is what the ball of radius r centered at x0 looks like. In the complex numbers, it just ends up being truly a disk centered at the value x0. So there's my center and the ball. So all points that the power series would converge at include everything within one radius of convergence of the center. And so if this center, for example, you can imagine this as like 1 plus I, and suppose the radius were equal to 2, for example, then something like, well, 3 plus I would be on the edge here. And we don't know about convergence there, but something like 2 plus I would be perfectly fine, and it would be inside of the ball, and everything would converge at 2 plus I. So that's what those look like. Let's just look at one example, everybody's favorite example of a power series without even me necessarily having to define what a Taylor series is. We can define one very specific power series called the geometric series, which is just the power series corresponding to an being constantly equal to 1, right? Because if I construct the power series where I would normally put an an in there, but if an is constantly equal to 1, then I'm just going to replace that an with the constant value 1. And then, in fact, this power series, I should say, centered at x equals 0, I would put a 0 in for that x0, and you would see everything reduced down to just the sum from 0 to infinity of x to the nth power. This is kind of everybody's favorite power series to work with, and you can actually go ahead and evaluate what the series would look like as a function by using your exponential rule for sums. Let's recall what that rule said. It said something like a to the nth power, that's not a sub n, that's a to the nth power, is equal to a to the nth power divided by a minus 1. And so in this case, if you want to take the limit of the upper bound to infinity, you're going to have to take this n all the way up to infinity and then subtract when it's at 0, the lower bound here. So I subtract at 0, a minus 1. As long as this value of a were between -1 and 1 right away, a number like 0.5 to the infinite power just tends to 0. And so this term falls off. You get -1 divided by, well, a minus 1, or if I flip the denominator at the price of the negative sign, I get 1 over 1 minus a. But of course, if I replace that a with an x, replace the a with an x, you get 1 over 1 minus x for the geometric series. So we could evaluate the series either like this as a power series or like this as a function, and they end up being one and the same. Now I have to make this very clear, they end up being one and the same so long as x remains in the interval -1 to 1. These intervals are incredibly important when you deal with power series. That interval is the ball of radius 1 centered at the center of this power series, which happens to be 0, right? A ball in the real numbers of radius 1 is just going to be an interval of length 2 because the diameter is twice the radius. And so it's an interval of length 2 centered at 0. That interval is going to be -1 to 1. Now, why does it make sense that I shouldn't be able to plug 1 in here? Yeah, I mean, you divide by 0 and you plug 1 in. If you plug -1 in, though, everything works out and you end up with what, 1/2? Why doesn't that work? Well, it kind of does and kind of doesn't, and there's a lot of very deep math, other mathematicians who have researched this, but this is the sort of math that you can only get excited about if you decide to become a math major and take some senior level courses. So, unfortunately, you're going to have to postpone wanting to plug a -1 into this geometric series and make sense of it. Instead, we're just going to say, make sure that you leave x within the ball that it actually converges. Now, if you wanted to evaluate, we can evaluate this at a few other points. We could evaluate g at 1/2, for example. That's me just plugging in 1/2 for x in the power series. What I can say about that is 1 plus 1/2 plus 1/2 squared, which is a fourth, plus 1/2 cubed, which is an eighth, and so on. If I add all those numbers together, well, what would that series actually terminate into? Well, it terminates to 1 over 1 minus 1/2, or 1 over 1/2, or 2. So you can say that the power series at 1/2 is equal to 2. That's okay because 1/2 is in that ball of radius 1. We do the same thing with -1/2, which would now alternate signs, right? Because -1 to the 0 power is a +1, to the first power is -1, squared is +1, cubed is -1, and so on. We're going to alternate all these signs, and now what is our value going to be? Well, it'll be 1 over 1 minus -1/2, 1 over 3/2, or we'll get 2/3 out of this. And you would see if you just decided to type these into your calculator and start adding them all up, you get pretty darn close to 2 in the first case, you get pretty darn close to 2/3 in the second case. So this does work, and you can think about it either as an evaluation on a function or as an infinite series, which is pretty cool. I make my two comments about, of course, if trying to evaluate at 1, that's going to be 1 added to itself infinitely many times. Of course, that's going to diverge out to infinity. Evaluating at -1 is just going to be 1 minus 1 plus 1 minus 1 plus 1 minus 1. Now that would diverge not out to infinity, but it just doesn't exist as a limit, even though you can make that lovely evaluation and get 1/2 over here. You can imagine kind of maybe averaging that over time. It's called a Cesaro sum, but we're not going to study that in this class, unfortunately. There are ways of thinking about it as a 1/2, but we just can't get there. Anyway, this is the geometric series, super famous, super useful power series. It ends up being centered at 0 with a radius of convergence of 1. Let's move on to what I actually care about for today, my favorite topic of Calculus 2, the Taylor series. A Taylor series is a very, very specific power series. It's specific in the sense that the sequence of the power series has been defined by the derivatives of a function at the center divided by the nth factorial. So it's a very, very specific power series where you're computing derivatives of a function evaluated at the center divided by a factorial. Now, I can't stress this enough because when I see students do Taylor series all the time, they make one super common error, and that's that they often forget to evaluate at the center. Students will just put an x in here and be happy. No, that is definitely x0, meaning x0 the center, and x0 right here. It's not a power series unless that's a sequence of numbers, not a sequence of functions. And so that needs to remain a sequence of numbers. That's what's going to give us the Taylor series. What's important about the Taylor series, as I've defined it here, there's nothing special necessarily about using a bunch of derivatives of a function for the coefficients of a power series. But what is special is the next theorem, which I'm calling Taylor's theorem, even though some people refer to Taylor's theorem as like a specific part of the proof of what I've got here. But I'm calling that theorem Taylor's theorem, which basically says, hey, if you compute a very specific limit of a very specific integral, now that looks terrible, right? We're doing an integral over the range from x0 to x. I mean, there's no surprise why that's the range there. You do the integral over the range x0 to x of specifically x minus y to the nth power over n factorial, and then you take n plus 1 derivatives of your function in the variable y, and you're integrating in the variable y. Okay, so if you're integrating in the variable y, then that, and that all get integrated. But in fact, this x and this x remain as variables. Very interesting. But this limit says, hey, if you take the limit of n, which happens to be the value here and the value here and the value here, if you take that n out to infinity, it shouldn't care about these variables of x that are hanging out. It should send everything to 0 no matter what. Now, there's a very specific thing that you have to test that we are absolutely not testing in this class because it's way out of the scope of what I would expect anybody in this class to be able to test. Something that could show up in like a real analysis course, definitely. But, you know, supposing that somebody else in the world has tested this for us and verified that a function inside of an integral of this type does tend to 0, what do we actually get out of the Taylor series is we get what I've drawn at the very bottom here, but let me just rewrite it in the center of the screen. We get that the Taylor series is not just a specific power series, it's a specific power series which is truly equal to the function whose derivatives we are computing. And that's a really, really fascinating idea. The idea that a function, this could be e, it could be cosine, it could be log of the square root of x squared plus 1 minus inverse tangent of 17x. And it says no matter what function I start with, as long as it satisfies, you know, my kind of tricky property down here, tricky property that we're not going to worry about for now, but as long as it satisfies that tricky property, I can actually rewrite the function as an infinite series of polynomials. That's kind of the point of this, polynomials against derivatives. But polynomials, we love polynomials. Power rules for integrals, power rules for derivatives. We can use quadratic formulas when they're quadratic. We can do so many things with polynomials that we absolutely cannot do with something like the inverse tangent function or the logarithm of the inverse tangent function, right? There are just some really tricky functions out there that none of us like to work with, but instead we would rather work with polynomials. That's what Taylor series says. That's what Taylor's theorem says. It says we can represent a function which is very much non-polynomial as a collection of polynomials. Now the downside is that it's technically an infinite collection of polynomials. We're not going to worry about that for now. We're basically saying, hey, this is a polynomial of infinite degree, but basically behaves like polynomials, and that's where we're going to see all of the power. So that's the Taylor's series and Taylor's theorem. There's my lovely proof of the theorem. Looks very intense. This next remark is basically me saying, hey, that really complicated property of the limit and the integral in Taylor's theorem, forget about it. The functions that you see in calculus as an undergraduate in calculus, you're good. You're going to be able to use Taylor's theorem for them. So, for example, we've got polynomials, the exponential, the sine, and the cosine. These are called analytic. And they're called analytic everywhere. What does analytic mean? Analytic just means Taylor's theorem applies. So if you hear people talking about analytic functions, what they mean is Taylor series representable functions. Now, what does everywhere mean? Everywhere means the radius of convergence is infinite. Or in other words, the series converges for all x in R regardless of the center. And so polynomials, exponentials, sines, and cosines, beautiful functions. You can't go wrong with those when it comes to Taylor series. Now, rational functions, a little bit trickier, right? It's not going to make sense to have a series that represents a rational function when rational functions, remember, these are the ones like x squared minus 2x plus 3 all over x cubed minus 10x squared plus 2x minus 5. Well, there's going to be some places where that denominator is equal to 0, and it's not going to make any sense to talk about the function wherever the denominator is equal to 0. So these are going to be analytic everywhere that they are defined, in other words, not dividing by 0. So don't try to represent this as a Taylor series where you divide by 0, because it's not going to work. There's no way that it should work. Something like the square root of x and logarithm of base a, including the natural logarithm, right? Log of x is just log base e. These are going to be analytic on all positive real numbers, so you can Taylor represent them on all positive real numbers. Similar to dividing by 0, right? Both the logarithm is undefined when you plug in 0. The square root function is undefined when you go negative. So like technically it's defined at 0, but like infinitely close to 0 on the negative side, also not defined. And so you can only really define these using the Taylor series on positive numbers. Something like your trig functions, but the trickier ones like tangent, cotangent, secant, and cosecant, well, each of these is dividing by 0 somewhere, right? Tangent is sine x over cosine x. Cotangent is cosine x over sine x. Secant is 1 over cosine x, and cosecant is 1 over sine x. So all of these divide by a function, and of course that could be 0 at some point in time. So as long as you don't try to define the Taylor series where they're dividing by 0, everything works out. So just don't try to do that. But otherwise, they're representable using the Taylor series. And finally, kind of the important thing that combines all of these together. How do I combine all of those together? Well, with composition. So that means something like e to the root x squared plus 1. That's a composition of the exponential, the square root, and then a polynomial x squared plus 1. Those are also going to be analytic under appropriate domains and codomains, right? Like I don't want to accidentally put a negative into a square root as long as I'm not working in the complex numbers. If I'm working in the complex numbers, ways around it, but you don't really want to put a negative into a square root by accident by composing in a poor way. But what this is basically saying in this remark is that as a calculus student, not as necessarily a professional mathematician, but as a calculus student, most functions have a Taylor series. So you can feel pretty good about writing down a Taylor series if somebody asks you to. Let's see what this actually means. We've got a collection of Taylor series here for all of our favorite functions. And I'm calling these the must-know Taylor series, basically because for me, these are as important as derivative rules. So I've got all 7 of these memorized because they're as important as derivative rules to me. I use them on a daily basis, probably more often than derivative rules, which is kind of insane. And so if you plan on continuing calculus, I really would advise that you memorize all 7 Taylor series that we see on the screen right now. And you think about them as new representations of functions we've already been using. So that's really why you should memorize these. If you like using the function 1 over minus x, if you like using the function e, if you like using sine, if you like using cosine, if you like using arctan, log, or x to a power, particularly a fractional power there, sometimes you want to use them, and yet you get stuck integrating them or differentiating them or finding their roots or something, right? That's hard to work with these functions sometimes. But what you can work with a lot more easily if you memorize all of these Taylor series instead is you can work with polynomials. And working with polynomials just tends to be easier. It really does. So these are new representations of functions we know and love. Let's look at a couple of these. So the one we already saw, this is called the geometric series, right? But you could derive its Taylor series. How do you derive a Taylor series? You compute derivatives and evaluate the derivatives at the center. Now it turns out that the center of these first 5, these are centered at x naught equals 0. How can I tell? Well, I look here and see what's the shift on that x. There's no shift on that x, so no also meaning 0 in this case. So there's a 0 shift on each of those x's. They're centered at 0. We've already seen the geometric series is just equal to x to a power constant sequence a. Now the geometric series will converge over the interval -1 to 1. The exponential function, if we write out its Taylor series, you can compute this as well, ends up being 1 over n factorial times x to the nth power. And that has an interval of convergence that's everywhere. You never have to worry about this one converging. It'll always work. You write down sine, and you write down cosine. These kind of are 2 sides of the same coin. They're a little funky looking, so let's actually talk about what's going on here. We have -1 to the n. -1 to the n alternates signs. right? Plus or minus, that's all it's basically saying, because when n is odd, you're going to get a negative sign. When n is even, you'll get a positive sign. But what's going on with the rest of it, this power 2n plus 1, let's think about what 2n plus 1 looks like. When n is 0, that's 1. When n is 1, that's 2 plus 1, that's 3. When n is 2, that's 4 plus 1, that's 5. When n is 3, 7, 9, 11, dot, dot, dot. These are just the odd numbers. And actually, you see in the factorial part, there are odd number factorials here. Okay, and then cosine's the other half of the same coin. We still have alternating signs, except we don't have odd numbers now. We in fact have 2n. So what is every number if you multiply it by 2? When n is 0, that's 0. When n is 1, it's 2, 4, 6, 8. These are the even numbers. And then the even numbers factorial down here. So if I were to write out these series for sine and cosine, you can think with the sine series, it's really saying it's what? Negative 1 to the 0 power all over 1 factorial, x to the first power, plus negative 1 to the first power all over 3 factorial, x to the third power, plus negative 1 squared all over 5 factorial, x to the fifth power, 7 factorial, x to the seventh power, and so on. Or if I actually write that out, that's x minus x cubed over 6 plus x to the fifth over 120 minus x to the seventh over 5040, and so on, right? So you get this kind of alternating odd-powered x's, but alternating signs to give you, what sine is actually equal to, kind of as a polynomial, right? You think about sine as a polynomial now. Same thing with cosine, right? You would get something like 1 minus x squared over 2 plus x to the fourth over 24 minus x to the sixth over 720, and so on. And so you can think about sine and cosine now as really like these even and odd powered polynomials. And that's the point of Taylor series, is to give you a new representation of these functions that you know and love. Finally, we've got this inverse tangent one here. An inverse tangent, if I write out a few of these terms, what's going on with the 2n plus 1, those are the odd powers again. But I don't have, in the sine case, you had something like the odd powers factorial. In the inverse tangent case, it's no factorial in the denominator. We also have the natural logarithm for your viewing pleasure. This one ends up being negative 1 to the n minus 1 over n, so there's no factorial there either. But what's happened over here? Why does it look like x minus 1 to the n? Well, these bottom two cases are actually centered at x naught equals 1. And so you can always find the center by looking at that shift, right? The shift by x is going to help you find the center. This last case of x to a power, really mean x to a fractional power, so x to the 1/3, x to the 27.8 or something. You can represent those using a Taylor series. Using this really is the binomial coefficient still, so like Pascal's triangle, but I'll put that in quotes because Pascal's triangle only makes sense for whole numbers. When you work with fractional numbers like 1/3 or 27.8, like I was saying, you just have to define these a little differently. You just define them. It's technically a ratio of falling factorials, right? If you remember your falling factorials, that's a falling factorial n over n falling factorial n. So just a slightly modified binomial coefficient going on there. Now, both of these cases of the log and x to a power are defined in the interval of convergence 0 to 2. And that's because they really have a radius of convergence of 1 and center at 1. And so your interval is on the negative side, 1 minus 1 gives you 0, and on the positive side, 1 plus 1 gives you 2. Okay, so that's, a good collection of Taylor series, and it's lovely to memorize those. Probably is going to do you more good than the next definition, but suppose that you actually want to compute these for yourself. How do you actually do this? Got a step-by-step process here. What we're going to do is we're going to start with a function f that's going to be, we're just going to assume it's analytic for this class. Nobody's ever going to force you to test whether or not it's analytic, but so you assume you can actually evaluate the function at this special point x0. You can compute the Taylor series centered at that point x0 by doing the following. You're going to have to compute enough derivatives. This is enough derivatives of f evaluated at x0 to recognize a pattern. Okay, that's going to be the kind of the important point here. So you'll just start calculating derivatives and start evaluating all of those at your specific center that you care about. Ideally, you can see a pattern. If you can see a pattern, then use that pattern to describe the nth derivative, right? If you've got n, and you notice a pattern, you should be able to describe an expression of n, which represents the nth derivative evaluated at your center. You're then going to go ahead and use that expression of n inside the definition of the Taylor series. It's going to go right here on top of the fraction, divided by n factorial, and then you just go ahead and include this x minus x naught to the nth power, as well as that infinite series. So So that's going to construct the Taylor series for you. Sometimes you won't be able to recognize a pattern. That's okay. I've got this remark here, right? Sometimes you won't be able to see a pattern. What you do then is you just write out a few terms. I really hope you can recognize a pattern. It's great to have pattern recognition, in math, but also in the entire real world to predict the future in some sense. But if you can't, not the end of the world. Often what you'll do is, that's your 0th derivative. You include your first derivative, your second derivative, your third derivative, and as many as you decide to actually compute at the center. And then you start dividing these by their factorials, because that's what they are supposed to be divided by. That 6 is like 3 factorial, right? And so 0 factorial just happens to be 1, so I omit it here, and that's fine. 1 factorial is also 1, so I've gotten rid of it here. 2 factorial is 2, so I've left it as 2. 3 factorial is 6. So you take those derivatives, divide by the factorial of the number of derivatives you've had, and then the Taylor series always says, hey, I'm also multiplying by the power of x minus the center, whatever that center happens to be, and that nth power up top, that's the number of derivatives you've taken. So in the case of 0 derivatives, what's x minus the center to the 0 power? Well, anything to the 0 power is 1, so forget about it. In the second case, I have 1 derivative, so I've taken it to the first power. 2 derivatives, I've taken it to the second power. 3 derivatives, it's to the third power, and so on. Just write out as many terms as you're comfortable with, and in some sense, that is the Taylor series. I mean, you get a lot of wiggle room with those 3 dots at the end that says, yeah, this keeps going on, I just don't know how to compute it. So that's fine with me. It's probably fine with most people. Definitely fine with physicists. They can take that as a jab. The physicists love their perturbation theory, which is basically finitely many Taylor series terms. Anyway, so if you can't recognize a pattern, not a huge deal, but we are going to try to recognize a pattern to finish out for today. So today we're going to analyze the Taylor series for sine, which, we already saw in this common Taylor series that I would love for you to memorize. The sine one is sitting right in the middle. Let's actually see if we can compute it using our step-by-step process. Let's center sine at 0. 0 is a very common place for us to center Taylor series. They actually have a special name, by the way, when they're centered at 0. These are called Maclaurin series, just because Maclaurin was also working on similar series. And one of them had to get one name and the other had to get the other. So specifically centered at 0, Maclaurin series, but we're just always going to call them Taylor series, or Taylor series centered at 0. And let's go ahead and see if we can find it for sine. We're going to take 0 derivatives of sine, which, by the way, happens to be itself. No surprise there. We're going to center it at 0, and so we're evaluating this 0 in my 0 derivatives. That's giving me a value of 0. This happens to be, f of 0 at 0. I'm going to take 1 derivative of sine, which happens to be cosine. I'm also going to evaluate that at my center 0, so I'm evaluating cosine at 0. Cosine at 0 happens to be 1, so that's f with a 1 derivative evaluated at my center. I'm going to take 2 derivatives of sine. That's 1 derivative of cosine, right, the previous answer I had. While a derivative of cosine is negative sine, I'm going to evaluate that at 0. So plugging in 0 to negative sine gives me 0. And so that's going to be f with 2 derivatives on it, evaluated at 0. Computing the third derivative, well, the derivative of negative sine gives me negative cosine, evaluated at 0. So I plug a 0 in. Negative cosine at 0 is negative 1. And so that's going to be f with 3 derivatives evaluated at 0. And now, ideally, I start to recognize a pattern. Why do I say that? Well, if you look at the fourth derivatives of sine, it goes back to itself, right? The derivative of negative cosine is a positive sign. So we are back to where we started, which means even though I ended up at negative 1 here, at f5, I'm just going to go back here. So 5 derivatives of f at 0, back there, 6 derivatives, 7 derivatives, 8, and then back up for 9 again. And so we just had this pattern of 0, 1, 0, negative 1, 0, 1, 0, negative 1, indefinitely for my derivatives evaluated at the center. Can I write an expression of n which computes this, right? In particular, what were the values of n that I cared about here? This was like n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, 5, 6, 7, right? So those specific values of n, how can I pair 0 to 0, 1 to 1, 2 to 0, 3 to negative 1, and so on? Well, the most natural way of doing that would be to start with this expression, which just alternates. This would start at when n is 0, we would get 1. When n is 1, we get negative 1. When n is 2, we get 1. And then negative 1 again. That's almost great, but it's not exactly what I needed. I needed zeros in the middle, right? I needed to alternate with zeros. So somehow I have to spread this to only the odd values of n. How do I achieve the odd values of n? Well, that's me running a piecewise function and saying, hey, n is odd when it happens to be 2k plus 1. And then when we have even values of n, I'm just going to go ahead and say that it's 0. And so in fact, this is my expression of n that I can use to generalize my pattern. And I'm just going to put the entire thing into the definition of f of n at the center 0 in my Taylor series. That's the numerator of the coefficients. And I could go ahead and write that Taylor series for sine just like this. By the way, this 0 is here because that is the center of the Taylor series that I care about. So I've got a 0 in there for now, and I could actually stop there. I mean, technically I've found a Taylor series. We can make it look prettier if we want to, and that's really where we end up going from here. So if I make it look a little bit prettier, what can I do? I can take this sum, and I can re-index the sum kind of in the event that n is equal to 2k, in the event that n is equal to 2k plus 1. So I'm going to re-index in the variable k, and I'm just going to replace, well, the n here I'm going to replace with 2k in the first case, and I'm going to replace it with 2k plus 1 in the second case. But that means I'm also going to replace, well, the upper value of f with, its value 0 in the first case, or negative 1 to the k in the second case. And in fact, this n gets replaced with 2k in the first case and with 2k plus 1 in the second case. That's really kind of a jumbled mess, but ideally you can see where all those terms are coming from. But now I have two sums. Notice this first sum just has a 0 in every term. A sum with 0 in every terms is equal to 0. So I'm just left with this sum. If I kind of rearrange that sum a little bit and make it look a little prettier, we end up right here. And this is exactly the infinite sum for sine, or the Taylor series for sine, that we saw in our must-know collection of Taylor series. And so that's pretty cool. We'll do one more example before we finish, because I know this video is really going on pretty long. It's really exciting. That's why it's going on so long. So we've got a Taylor series for the natural logarithm. So it's also coming straight out of that must-know collection of Taylor series. We're going to do it for the natural logarithm. Now, keep in mind, why don't we center the natural logarithm at 0? Well, if I tried to center at x equals 0, what happens is you just immediately get log of 0, which we already know is minus infinity. Even if you tried to do like the first derivative of the log, you get 1 over x, and trying to evaluate 1 over x at 0, you're still getting infinity. So you're kind of stuck not choosing 0 for the natural log. We're instead going to choose 1. Turns out 1's a pretty good value because if I do take the derivative, 1 over x, evaluating that at 1 gives me a very nice, very pretty answer, 1 over 1. So we're going to go ahead and center this function at x equals 1, and then we're going to go ahead and try to compute derivatives and notice a pattern. So if I take 0 derivatives of the natural log, not a surprise, that is the natural log. We're going to evaluate that natural log at 1, so I'm going to put a 1 in here, giving me log of 1 is 0. That's going to be f with 0 derivatives evaluated at 1. If I take 1 derivative of the natural log, that's 1 over x. If I evaluate that at the center 1, and I'm going to put a 1 in there, I'm getting 1 over 1, I'm getting 1 is f of 1 evaluated at 1. We go ahead and take 2 derivatives. That's 1 derivative of 1 over x. 1 derivative of 1 over x is going to give me negative 1 over x squared. If I evaluate this at 1, that's negative 1 over 1 squared, also known as negative 1. This is f with 2 derivatives at 1. If I take 3 derivatives, that's 1 derivative of my previous one, which was negative 1 over x squared. It's going to give me a positive. The 2 comes into the numerator, and then I'm getting x cubed in the denominator. Evaluate this at 1, I'm going to get a 2. That's going to be f with 3 derivatives at 1. 4 derivatives, I'm taking 1 more derivative of 2 over x cubed. That's going to give me, well, the negative 3 is coming by to multiply everything. So 2 times negative 3 is negative 6, all over x to the 4th. Evaluate this at 1, I'm getting negative 6 over 1 to the 4th. I'm getting negative 6. That's 4 derivatives of my function at 1. If I do the next one, I'm getting a positive 24. Now, you may not be able to notice the pattern between 0, 1, negative 1, 2, negative 6, and 24. Let's think about maybe not including this initial 0, because that's actually going to play a special role here. And let's forget about these negative signs. Let's just look at the sequence 1, 1, 2, 6, 24. That sequence, of course, does have a very good pattern. Of course, I've already displayed it for you on the screen. 1 is 0 factorial, 1 is 1 factorial, 2 is 2 factorial, 6 is 3 factorial, and 24 is 4 factorial. So we can actually find, at the very least, we can find a sequence for all of these numbers without maybe the alternating plus minus signs. But we already have seen a few times how to alternate a plus and minus sign. It's always with negative 1 to a power, right? Negative 1 squared is positive 1, negative 1 cubed is negative 1 and so on. It just alternates correctly. We have to include the n minus 1s here. Why do we have to do that? That is where this initial 0 plays the role, right? Because here's a 0, 0, and that's a 0 there, but 0 is not equal to 0 factorial, unfortunately. It's this 1 that's equal to 0 factorial. And so when this power here is 1, we actually want to recover the 0 factorial. And so if I plug in a 1 for n, I want to get 0 factorial. That's why I have to subtract, because if I plug in a 1, then I get 0 factorial. So it turns out that is going to be my kind of expression of n, which describes all those terms. And I just go ahead and grab that expression and plug it in for this term, f of n evaluated at my center in my Taylor series. So I plug it in for that. And when I do plug it in for that, I could, as always, leave my Taylor series like this. It's nice and ugly. By the way, here's my center. I've evaluated at the center being 1. It's a little ugly, and I've had to include the n equals 0 term separately, so I started the infinite sum at 1, because we calculated all the way up above that it was 0 at 0. So I've included that separately because that doesn't really work with my pattern. But other than that, this is technically a valid Taylor series. We can go ahead and simplify it a little bit though. So I'm going to go ahead and simplify this Taylor series. How do I want to simplify it? Well, I've got a factorial n minus 1s here. I've also got a factorial of n's. We've kind of seen this in the past where the factorials play really well with each other. I'm just going to be left with an n in the denominator left over. And so what we actually get out of this is I've dropped the 0 up front and we get this infinite sum, which starts at 1 and ends at infinity of an alternating negative 1 to the n minus 1 divided by n, but there is no factorial here. Now we're going to stop there because it's been a long video. I've got really exciting things to say about generating functions, and in fact a lot more applications too, because they just keep going on and on with the Taylor series. I really can't give it enough praise. We're going to stop there, give you a little bit of time to digest everything you've seen, and then we'll hop in at the next one with so many other cool ideas. See you then. Bye.